Welcome to our introduction to electromagnetic compatibility, or EMC. In this session, we'll explore the concept of coupling mechanisms and their role in how electromagnetic interference, or EMI, can impact electronic systems. We begin by examining the pathways through which disturbances can infiltrate our systems. The displayed diagram clarifies that an interfering signal has a specific source and a defined path that it follows. The noise source can be natural, such as lightning strikes or cosmic noise, or man-made, including broadcast stations or the clock trace of your electronic system. These noise sources are recreated by EMC engineers in lab settings to study their effects and develop mitigation strategies. The coupling path is the route taken by interference to enter and affect our systems, and understanding this path is crucial for effective interference mitigation. Interference coupling is categorized into galvanic, capacitive, inductive, and radiated. Galvanic involves a conductive connection. Capacitive and inductive are near-field interactions, while radiated coupling occurs over larger distances in the far field. Before we go on, let us clarify what we mean by a near or far field. The graph shows a typical propagation of an electromagnetic field. The wavelength is designated by the symbol lambda. The near field is defined for distances smaller than lambda over 2 pi. The far field applies to distances greater than lambda over 2 pi. But keep in mind that this is just a coarse rule of thumb, as this depends on the geometry of the antenna. Back to our diagram. The receptor or victim of interference, also known as the device under test, DUT, is the component within your system vulnerable to EMI, which we aim to protect. In the lab session, you will identify interference pathways, understand the benefits of minimizing loop areas, and compare various methods to reduce coupling effects. Now let's dive into a prevalent coupling type in EMC, galvanic coupling. Galvanic coupling is characterized by two circuits sharing the same electrical path, like in this case, a common ground connection. This means that disturbances in one circuit have a direct effect on the other circuit. Despite common connections to ground, it's important to note that this does not imply identical potential across the system due to the impedance of the ground plane. To gain a more detailed understanding of galvanic coupling, please view the next video in this series.